that photo is from 30 years ago, and what I look like now is what happened because of what I'm going to talk about to you today, the statistical modeling, and I'll focus on intensive longitudinal data, which is sometimes called ecological momentary assessment data, and in particular how this helps us to model not just the mean structure but the variance structure in a class of models known as mixed effects location scale models. So EMA studies are a way of collecting intensive longitudinal data. I started getting involved in these studies a while back, and the way they work is that subjects provide many reports on events and experiences over their daily life in a period of a week or so. Years ago, we used to collect such data with electronic diaries, Palm Pilots, PDAs, but these days pretty much everything's on smartphones. And the idea behind these kinds of studies is that you get particulars of experience in a way that's not possible with more traditional longitudinal designs. So you try to get measurement as things happen across time in these kinds of studies. And the reports that you get, they could be time-based, they could follow a fixed schedule. Let's say every day you might get a report, or they may be randomly triggered or even event triggered. The data I'll be speaking of today, the example is really more of a fixed schedule scenario, but in other papers I've worked on, we've looked at all these different kinds of reports as well. Now, I went to Pubmed Central and I typed in ecological momentary assessment, and I got this nice plot here that kind of gives the impression, wow, you know, this is just going off the root. It's like exponential growth across time. Well, I've presented this before, and people in the audience have said, well, you could type anything into Pubmed Central and you'll see this kind of pattern. And so sure enough, I went back to Pubmed Central and thought, well, what can I type in that, you know, that's not really used too much anymore? Canonical correlation. You know, you type that in, you see this kind of pattern. Discriminant function analysis, you see this kind of pattern. You can type in almost anything, but I talked to my colleague, Robin Mermelstein, and she suggested I type in this instead, lobotomy. Well, you type in lobotomy, you don't get that same pattern. But notice, what's interesting here is they're obviously in the 50s and 60s, this was an area of some research, but then it died down. But then in the mid 70s, it kind of came back. Anybody have an idea what that might be attributable to, this rise in lobotomy publications in the 70s? Well, thing that sometimes comes to mind is the Jack Nicholson movie, One Flew Over the Cuckoo's Nest. So that's one possibility there. Anyway, so the point is that these kinds of studies are really growing in their application. And so what I'm going to talk about today is statistical modeling of such data. Okay. So there's lots of data here in such studies, many subjects and a lot of within subject information. And so what it allows us is a lot of different modeling possibilities. So we can look at person level and occasion level predictors of occasion level outcomes. And the response might be different depending on the context or environment. So subjects might respond very differently, for example, when they're alone or with others. And we can include this kind of these kind of covariates in our models. And one additional thing that's really possible in data sets like this, where you have a lot of data within subjects, is that you can model not just the mean structure, but also the variance. And that's what I want to focus on today, and look at the effects of covariates on both the between and the within subject variance. And so why do we want to do this? Well, this can help us learn about why is it that subjects are similar or different from each other, subject heterogeneity. So as we'll see, it can be the case that different groups of subjects are more similar to each other and other groups of subjects are more disparate from each other. That's the between subject variance. We can also look at the within subject variance. We got 30 or 40 measurements within a subject. We can characterize subjects in terms of how stable they are and how erratic they are. And in particular, this is really what got me into this area of modeling, because I was working with people who were working on smoking studies, smoking researchers, and they would tell me one reason that people say they smoke cigarettes is to stabilize their mood, for mood regulation. And so I came to realize, well, that's really more about the variance than about better mood per se. And so that's what led to this. And it resonates with a paper published by Ray Carroll a while ago in Biometrics, the idea that variances are not always nuisance parameters. All right, so let's start with the equations. Everybody wants to see the equations. Let me start with a very standard multi-level or mixed effects regression model, or linear mixed model, or hierarchical linear model, whichever term you want to use for this kind of model. And so we're going to model an outcome from subject I on occasion J. And again, the kind of environment here is we've got, say, a few hundred subjects, and they're measured over the period of a week or many weeks. And so we might have 20, 30 measurements on a subject. And so that's J, the time point. Well, subjects have different numbers of observations in these studies, so N sub I there. And we're going to use first, to begin, a very classic linear mixed model where we have covariates X. We're interested in their coefficients, the betas. And we have a random intercept in the model to account for the differences across subjects, and an error term. And so the random effects here characterize the between subject variance. How homogeneous, how heterogeneous are subjects. The residual or within subject variance is really about how consistent, how erratic are the data within subjects. Okay, so very classic kind of decomposition of the variance, the between variance, the within variance. Now, let's consider that model if we don't have any covariates, just to make it very explicit here. In this case, the random effect, epsilon I, really represents the subject's mean. Okay? Now, clearly, it's a deviation from the intercept beta naught, but it reflects a subject's mean. So this model is saying subjects might be higher, some subjects might be lower. If subjects are very similar to each other, then these epsilons will be close to zero, and the subject variance will approach zero. In the more typical case, subjects are different from each other, the random effects are different from zero, and the between subject variance increases from zero. Okay, so the between subject variance tells us how different are subjects from each other. They characterize the heterogeneity across subjects. In contrast to that, the residual, the error term, is the subject's error time J. They represent, for a given subject, the deviation of the outcome variable relative to a subject's mean. Okay? So if subjects are very well fit by their mean, then these deviations are close to zero and the residual variance gets small. If subjects aren't so close to their mean, the residual variance gets large. Okay? So the residual variance, so within subject variance, indicates how the data vary within subjects. So I'm going to use this term heterogeneity to refer to the between variance and really erraticism or consistency to think about the within subject variance. Okay. And this is, I want to model both of these in terms of covariance. So to do so, what I'm going to posit are log linear models for these variances. Okay, so why log linear models? If I do it this way, no matter how I do the modeling, I'll always get positive variances. Okay, so this is very similar. I'm using an exponential here to link the covariates to the variance. So here I have a between subject variance I'm going to characterize in terms of covariates. They could be the same as the X variables, but here I'll just say there's some variables U, let's say, and then there are regression coefficients. Okay, so this part of the model will tell us why is it that subjects are similar to each other or different from each other? What covariates might explain that heterogeneity? Similarly, for the within subject variance, I'll have some covariates W, their regression coefficients tau. Again, I'm using the exponential just to ensure that the resulting variance is positive. Okay, so again, it's a log linear model for the variances. And in the within subject variance, what I'm able to ascertain is whether covariates are related to how consistent a subject responses are or how erratic they are. Okay, so in these models, I'm going to have covariates. Now, both covariate vectors will have usually a column of ones for the intercepts. And just to make note that the I and J subscripts on the variances just indicate that these variances can change depending on the covariates and their coefficients. And the exponential function just is here to ensure that we always get a positive variance in this modeling. So it's exactly like when we model count data and use Poisson regression, there's a log link to ensure that the resulting count in that modeling is always positive. It's the same idea here, but just applied to variance. Now, an additional aspect of the model that one can do is to realize that the within subject variance can also have an individual component. Okay, so here I'm going to add a random effect, omega I, that's subject specific. It's a random effect, so it has a distribution in the population. I'll assume normal and scale variance here, sigma squared omega. So what's the idea here? Well, I'm going to be modeling, for example, if I'm modeling mood from an EMA study, some subjects are very consistent, some are erratic. Now, covariates might explain some of that, but there's an individual component as well that is over and above the effects of covariates. That's precisely what the random effect is going to get at. Okay, and so here we have these second kind of random effects, these ones related to the within subject variance, and I'll refer to these as scale random effects. They indicate how a subject differs in terms of the variation in their data. Okay? And they're distinct from these more usual, I was going to say normal, but it has implications in statistics. So more usual location random effects, the upsilons, which tell us about how does a subject differ in terms of the mean of their data. Okay, right? So if we go to this classic mixed model here, the upsilons here are basically telling us how do subjects differ in terms of their means. Okay, that's what the random effects in the mixed model is about. How do they vary in terms of their means? What we're adding on to that now in the within subject variance is saying, how do people vary in terms of how consistent or erratic they are? That's the scale random effects. Okay, so I have these two different kinds of random effects in this model. All right. Well, really, one can also think of it, it's like a multi-level model of the within subject variance. Okay. So here I have on the left-hand side of the equation, the log of the within subject variance, and that's equal to some covariates, W times their coefficient tau, and a random effect. Okay. So this equation here really mimics the usual multi-level model of the mean structure, which is given here, right? Same kind of idea. Okay. And it really relates to something you might have seen in the literature. I've sometimes seen this. People have interest in modeling the variability in subjects. And so what they sometimes do is they'll let's say you've got this data, you got 100 subjects, you got 30 observations. You calculate for each subject the standard deviation. Okay? Now you use that in a second stage kind of model to see, oh, is the standard deviation different for, say, males and females, or depending on the age or something like this. Okay? Well, that's been done in the literature, and that's an idea. That's what I'm positing here. However, in this second stage kind of approach, it's treating like all these standard deviations like they're equally precise, but clearly that's not often the case. Some might be based on less numbers of problems or more. It doesn't recognize that these are estimated quantities if one did it this way. And furthermore, it doesn't allow for the influence of occasion level predictors. Okay, so in spirit, this sort of second stage kind of approach, you know, it has a similar sort of idea, but doing it within the multi-level model of the variance, I think it has got certain advantages that we're going to use. And ultimately, we use multi-level models for mean. Why not for variance? Okay. So here's a picture, really, of what the model is doing. Okay. So the solid line essentially represents the mean. Okay. The mean across subjects. Okay. All right, so that's really the X beta part of things in our regression model. Okay, so what covariates are related to the mean response of the outcome variable. Okay, so that's the typical regression part. Now in this mixed model, we have here, I've got one subject above, one subject below for illustration. And the spread of those dotted lines represent the between subject variance. Okay? So that's what we're also going to be modeling it. Why is it, let's say, that older people are more different from each other than younger people? something like that, in terms of their means. That's what the between subject variance modeling is going to get at. What is related to heterogeneity, homogeneity across subjects? Finally, we can additionally model the dispersion of the points within a subject. Why is it that this person on top is highly erratic and this person on the bottom is very consistent? What covariates might explain that? Now, when I use these kind of plots, I was trying to think of some good examples of, you know, who's a very erratic person, who's a very consistent person. And you saw the slide to begin this. I'm rather up there in age. So I was thinking of 1970s tennis. And in 1970 tennis, there were two particular tennis players that were either like this or like this. So one person I have in mind is highly erratic. Anybody know which tennis player I'm thinking of from 1970 tennis? Highly erratic? You can speak up if you like.
John McEnroe.
There we go, John McEnroe, of course. He would be throwing his racket, screaming at the ref, you know, displaying all kinds of erratic behavior, right? On the bottom, we have somebody who's very stoic, very consistent in their mood, let's say. Who might that be in 1970s tennis?
The Russian, I've forgotten his name.
Stephen Edberg.
Oh, I was thinking of Bjorn Borg.
Bjorn Borg.
Yeah. So that's the idea here. But now here's the thing. You might say, well, you know, country of origin might explain the difference between McEnroe and Borg. And I would grant you that there might be an effect in that people from Sweden might be a bit more consistent than, say, people from New York. But I have to think there's some people in Sweden that look like McEnroe a little bit, and people in Sweden, or sorry, US, who look a little bit like Bjork. So there's an individual component as well as country of origin, let's say. Okay, so that's the idea, is that covariance can explain some of the reasons, but there's individual components as well. Okay, so this picture really is trying to get at what the model is about. Modeling the mean, modeling the between subject variance, modeling the within subject variance. And really what allows us to do this is the fact that we have a good number of subjects in such studies, so we can model the between variance. And then also within each subject, we've got a fair amount of data within the subject, so we can model the consistency, the erraticism, the within subject variance. Now you might say, how do you estimate these models? When I began in this endeavor, I was using, and I still use to some extent, SAS, Proc, NL mixed. It's a nice procedure in SAS, and we, with my student, we have a recent paper that describes how to use NL mixed to estimate these mixed effects location scale models. And here's just a skeleton of the code. And I just put this up there to show you it's not really that hard. It only involves a little bit of coding. And additionally, what I've worked on is a freeware program that you can access if you like. It's accessible also via R and also via Stata. It's called MixReg Location Scale. And all of these approaches I have on this slide use full maximum likelihood estimation to estimate the parameters and to integrate over the random effects. They use a numerical quadrature in the solution. Okay, so this is the sort of a frequentist approach to this. Well, having said frequentist, you know what's coming next. There's also Bayesian approaches that one can take to estimate such models. And there's been a number of articles in the literature describing use of various Bayesian software programs, WinBugs, JAGS, StatJR, STAN, and then also SAS, Proc, MCMC. So there's a number of ways actually of estimating these mixed effect location scale models that one can utilize. I provide in this slide, I've got all these references as well. So if you have interest in pursuing this, you can, because many of these articles have sample code provided so that you can try the procedures out. All right, well, let me now apply it to a data set. And this is one that I was involved with Bonnie Spring, who's a psychologist at Northwestern University here in Chicago. And we published papers on it a while ago. What we've looked at more recently is this question of modeling the variance. And that's what I'll share with you today. So in this study, there was about 200 adults that had unhealthy levels of sedentary leisure time, and as well as fruit and vegetable intake, saturated fat intake, and moderate to vigorous physical activity. Okay, so we recruited such subjects, and they were randomized to 4 different treatment arms. In one arm, they were encouraged to increase their fruit and vegetable intake and also their physical activity. In a second arm, they were encouraged to decrease their fat and decrease their sedentary behavior. In the third arm was kind of a mix, decrease fat, but increase physical activity. And then in the fourth arm they were encouraged to increase their fruit and vegetable and decrease their sedentary. We were wondering which of these approaches led to better outcomes. Clearly, the standard approach that you often hear is the first one. You should increase fruit and vegetable, increase physical activity. But we were wondering if these other encouragements would produce better or worse results. Now, in this study, we got quite a few measurements per subject via accelerometer for the physical activity and for the sedentary behavior outcomes. And then they also recorded diet, which gave us diet outcomes that I'm going to be looking at as well. So strictly speaking, this is not an ecological momentary study in the sense that they weren't given a smartphone, and so the data didn't come to us that way. But it is an intensive longitudinal study in the sense that we have here quite a few measurements per subject, so up to 35 measurements per subject. And so that's what we'll look at today. Now, the measurements were obtained across 3 periods of the study. There was a baseline phase of 2 weeks. So we got approximately 14 days on these outcomes during baseline. Thereafter, there was a week in which the goals for these behaviors were set to about 50% of the final level. We call that RX1. And then after that, there was 2 weeks in which the goals were at 100% of their final level. So that's what gives rise to these up to 35 measurements. We have 2 weeks during baseline, we have a week during RX1, we have 2 weeks during RX2. All right, so what we're going to do today is to compare these different arms when the particular behavior was encouraged versus not targeted, and look at the effects both in terms of the usual mean outcomes, but also in terms of variance. And this paper that I have listed on the bottom in Health Psychology, that's an EPUB currently, describes this extended analysis involving the variances. Okay, so the papers on the top were really where we just looked at the usual kinds of mean responses, but this latter paper has additionally looked at the effects of things on variance, and that's what I'll share with you today. Okay, so here what I'm going to share is we did separate analyses on each of the 4 behaviors that were being measured: physical activity, sedentary behavior, fat intake, and fruits and vegetable. We have MVPA in minutes, we have sedentary behavior in minutes, we have fruit and vegetable consumption in terms of numbers of servings, and then saturated fat, we have it as percentage of daily calories. Now, in doing the analyses, what I'm going to do here is to take a square root transformation that helped to normalize the distributions of these outcomes. Now, in the analyses I'm going to show for each of these behaviors, what I compared were subjects that were targeted in terms of that particular behavior versus those that were not. For example, on the analysis of physical activity, what I compared were the 2 arms of the study in which they were told or targeted to increase their level of physical activity, and compare that to the 2 arms in which those were not targeted behaviors. So in each analysis, I essentially have a binary grouping variable. Was that particular behavioral targeted or was it not targeted? Now, time I'm going to use here in a very simplistic way. Just look at it as a linear effect across these 3 time periods, just coding it 0, 1, and 2. And so here in particular, what's of greatest interest is the group by time interaction. So does targeting the behavior change the response across these 3 time periods, both in terms of the mean and then also in terms of especially the within subject variance. Okay? So what we're interested in learning about is, does targeting, for example, moderate to vigorous physical activity, does that increase the level of physical activity? And also, does it increase the consistency of physical activity across time? So not just looking at the level, but also the consistency of the variable. So really, here's the mixed model I'm going to be describing. Again, it's MELS for mixed effect location scale. In terms of the mean part of thing, I'm going to have this behavioral outcome from subject I at time point J. I've got 3 very simple covariates, just period coded 0, 1, 2. Group, just was the behavioral targeted or not, and then group by time interaction. Again, I'll just have a random subject intercept and then a residual term. And then I'll model those in terms of the same covariates. Okay, so with the between subject variance model, what I'm addressing is what might explain the subject homogeneity, heterogeneity in their means across group, across time, and then group by time. Similarly, for the within subject variance, is it the case that subjects get more consistent, let's say, across time? And is that different depending on whether the behavior was targeted or not? So that's really the group by time interaction here. What can explain the consistency, the erraticism, let's say, in physical activity? All right, so that's the, this slide here on slide 16, very classic linear mixed model. Again, what we're adding to it is really what's on slide 17, which additionally models the between and the within subject variances. Now, let me say a little bit about the coefficients we get from the variance model, try to give a more concrete interpretation of it. Okay. So here I've written out the model that I'm positing for the between subject variance. Okay, so I have these 3 covariates, time, group, and group by time. So when time or period is equal to 0, this model would equal the following. For the non-targeted group, that's the group where the group variable is coded 0, the model would just simply be the exponential of the intercept parameter. And for the targeted group, we would have the exponential of alpha naught plus alpha 2. So if I take the ratio of those 2 variances, what I see here is that if I exponentiate the coefficients from the variance model, essentially what I have is a variance ratio interpretation. Okay? And again, this kind of resonates with Poisson regression. In Poisson regression, when one exponentiates the regression coefficient, what do we get? We get incidence rate ratios, right? Because it's basically a ratio of the rates per unit change in the covariate. Okay, so it's the same idea here, except it's not the rate, but the variance that's the ratio. So if we exponentiate the coefficients in our variance modeling, we get rate ratio interpretations that basically tell us the ratio of the variance per unit change in the covariate. So in what I'm going to show, I'm going to express the variance estimates in the exponential format to give us this variance ratio interpretation. And so here shows some plots that I used. Stata has coefficient plot, this kind of nice macro program that shows the results here for the mean effects. Okay, so let's go through these one by one. On the top left, I have physical activity. So that's my outcome. And what I have going down are my 3 covariate effects: the time effect, the group by time. Okay, so in these models with interaction, the main effects are the effects of those variables when the interacting variable equals 0. So the period effect here is the effect of time for the non-targeted group. Okay? And what we see in terms of the mean is that they increase their mean of physical activity across time. The group effect would be the group difference when time equals 0 during the baseline period. Okay, so there's no significant difference there between the groups. The thing we're most interested in is the group by time interaction. Okay? And what this shows is that the group that was targeted to increase their physical activity, they actually did so to a much greater extent across time than the non-targeted group. Highly significant result. And so on this metric, it's an effect of 1.75 or thereabouts. We see a positive effect here on physical activity. Turning this fruits and vegetable, get a similar kind of pattern. Okay. Again, there's a period effect that's for the non-targeted group. They are in fact increasing fruit and vegetable intake. There's a bit of a difference between the groups at baseline, but there's a very strong group by time interaction, meaning that if they were targeted to increase their fruit and vegetable intake, they did so across the 3 time periods to a much greater extent. Now, for the 2 not so good behaviors, sedentary behavior, for example, we see it kind of an opposite pattern. What we would like to see here is that they decrease these things. Sedentary behavior, saturated fat. Okay, so again, period effect here, that would be for the group in which the sedentary behavior is not targeted. Well, they do decrease it, but the group in which it's targeted, it's a highly significant group by time interaction. Similarly for sat fat. Now here what is one that's kind of interesting. Here the period effect is pretty strong. So really both groups are diminishing their saturated fat intake across the 3 periods, but the group that was targeted does so to a greater extent. So in terms of the mean effects, and this is what we reported in the earlier papers, there's a good effect of targeting the behavior really in terms of all 4 of these behaviors. You target the behavior and you see an increase in the good behaviors. You see a decrease in the behaviors that are maybe not so good in terms of the means. Okay, so that's not an unusual story or something that's readily obtained with more standard statistics. Now here show the variance effects. First, I'm going to present the between variance results and then the within. In many ways, we're more interested in the within effects. What explains the consistency or erraticism? But let me just go through the between effects here. Okay, so here I've represent these as variance ratios, exponentiating the estimates so that a value of 1 would indicate a non-significant result. So here what we're seeing for physical activity, for example, is a significant period effect that's positive. Okay. So what you're seeing is across time, subjects are getting more heterogeneous, essentially, in terms of physical activity by a factor of about 1.25 per unit of period. The other 2 effects don't come out to be statistically significant, the group effect, the group by time. For fruits and vegetables, there actually I had some problems estimating the interaction. So here it just has the model with the period and the group effect. And here again, with the period effect, what you're seeing is that across the 3 periods of the study, people are becoming more different from each other. Okay, so presumably some people are engaging in behavior to a great extent, some people are not. Here there's, if the group was targeted, there's a reduction in the between subject variance, which would suggest that those that were targeted, they're more similar to each other than the ones who were not targeted. And then for the behavior, sedentary behavior across time, what we see is that subjects get more disparate, more heterogeneous. The other 2 effects are not significant per se. And really with sat fat, we get again an effect that across time subjects get more heterogeneous. So really in terms of all 4 behaviors, in terms of the between subject variance, kind of the message is as time marches on, subjects get more heterogeneous. Okay, so this is something you often see with longitudinal data. You start the study and you look across time, the variance increases across time. Now, here's the results of the variance ratios for within subject variance. So these really are about consistency, erraticism in terms of physical activity, fruits and vegetables, sedentary, and sat fat. So physical activity. Again, I've exponentiated, so if it crosses 1, it's not significant. So what we're seeing for the group by time interaction is a reduction of the within subject variance by a factor of about nearly 80%. So per period, as we go from baseline to the first period to the second, the group that was targeted to increase their physical activity, they're getting more consistent in their level of physical activity by about 80%. So take that into account with regard also, here's the mean effect. Okay? So they're increasing in terms of their mean, but not only that, their consistency in the behavior is also enhanced. The responses are getting more consistent. Similarly, we see a same kind of pattern for fruits and vegetables. Okay? No significant effect for period, for group. Okay, that's a bit of a group difference at baseline. But the thing that really stands out is the group by time interaction. So in terms of the mean, what we saw for fruits and vegetable was the group that was targeted, they increased their level of fruit and vegetable consumption. Now what this is saying is they're very consistent in that behavior. So they're consuming fruits and vegetable at a higher level across time, and they're doing it to a more consistent degree. And here it's a factor of about 50%. So the variance for the targeted group is about 50% relative to the group that was not targeted. For sedentary behavior, what we see is that, again, group by time interaction. Okay? There's a period effect, so there is a reduction in sedentary behavior erraticism. They're getting more consistent across time, both groups, but the group in which it's targeted gets so to a greater extent. And similarly for fat. Okay, so what's remarkable here, I think, is the consistency of the effect on the variance, on the within subject variance. Namely that for all 4 of these things, what you're seeing is that if the behavior is targeted, not only do they do better in terms of the mean, they do better in terms of the within subject variance. They are getting more consistent in these behaviors. Now, let me just show as an example how we can take the estimates and see what they tell us in terms of raw numbers. Here I've got the estimates of the mean model for moderate vigorous physical activity. Okay. And here what I just use those beta coefficients, plugging in the 2 values for group, the 3 values for period, to get what are the estimates based on the model here on the square root metric. And then if I square those, I get it on the metric of minutes. What you see is that for the non-targeted group, they're pretty flat across time. Okay. For the targeted group, in terms of the mean level of physical activity, they increase quite a lot. Okay. So the MVPA mean level is increased across periods for the targeted group, and for the non-targeted group, not so much. Well, I can do the same thing for the variances. Here show similar kinds of calculations for the between subject variance for the 2 groups across the 3 periods. Okay. So again, what I do here is I first use this to give me the estimate on the square root metric, then I can square it to give the minute metric. And what you see is that for the group in which they were not targeted, they get more disparate from each other across these 3 periods to quite a great extent. On the other hand, for the group in which they were targeted this behavior, MVPA, they're pretty consistent, similar to each other. I shouldn't say consistent. They're pretty homogeneous to each other. Okay. So not only, so what this is showing is the effect on the mean. And what this is saying is that across time, if they were targeted, they're really not that different from each other. Finally, we can look at the within subject variance. Are they doing this consistently? Are they doing this in an erratic manner? So again, I estimated what the model provides for the 3 time periods for the group non-targeted, for the group targeted. Okay, and then I again, this is on square root metric. So if I square, I get on minute metric. What you see is that for the group that's not targeted, the variance is it goes down to some extent, but it really goes down for the group that's targeted. So they're much more consistent in their physical activity as time goes between baseline, first treatment period, second treatment period. So the MVPA consistency is increased, the variance is decreased across periods for the targeted group. Finally, what I'm going to show is we have this random effect of scale, and it's kind of like interesting part of the model that maybe you haven't seen before. And what I plotted here was I took a look at a subject on top who had a very large random effect scale estimate. So these are kind of like z-scores. They're standard normals. And so this person has a scale of 2.2. Their location, their mean effect is pretty close to the mean of 0. If you look at this, and the y-axis here has the square root of physical activity, you can see that, you know, they're pretty consistent at baseline. They're pretty consistent at the first follow-up, but then they really explode in terms of their level of physical activity. So quite a large variance there. And if I contrast that to this other subject who has a mean estimate that, again, it's not so far from 0, but their scale estimate is like -2. First of all, notice on the y-axis here, it goes from 0 to 12, whereas this first person was 0 to 30. So at baseline, their responses are basically in the 0 to 7 range. At the first follow-up, they're pretty darn consistent. And at the final follow-up, they're also very consistent. Okay, so this is just to give you a flavor of what this random effect of scale is really getting at, which is the degree of within subject variance at the subject level. How consistent is a subject? How erratic is a subject? And that's what it's picking up. Now, if you look at this plot, you might say that, well, it also looks like the scale might be changing within subjects across time, such that for this subject, it's growing across time. Maybe for this subject, it's diminishing across time. And that's something that we've been investigating further, is to have not only just a random intercept for the scale, but additionally a time effect there as well. And certainly these plots kind of give that suggestion. Okay, so finally, I'm almost at the end here. What I'd like to argue is that this location scale analysis is kind of an example of what I think about as the golden rule of statistics. So one person's error term is another person's career. So this modeling of the variance, right? If I didn't do this, where would it be? It would be in the error term, basically. So what I'm trying to illustrate is that there's some interesting results there that one can glean from the data and to actually model, and that's the basis of this slide. So to summarize, as we know, for longitudinal, for multi-level data, these kinds of mixed models, multi-level models, HLMs, you know, very common standard of modeling for longitudinal data, and they're also very useful for intensive longitudinal data. But hopefully what I've convinced you of is that with intensive longitudinal data, you can go further. And you can consider modeling not just the mean, but the variances, the between and the within. And I think that these answer some interesting scientific questions that previously we might not have paid such close attention to. Why is it that different groups of subjects are more or less homogeneous? Why is it that different groups of subjects are more or less consistent? What covariates might explain those things? Now, here what I've presented is a model in which I have just a random intercept in both the mean and the variance, and we've worked on some generalizations of that to allow multiple random subject effects for both location and scale. So the idea is you have intercept and slope, and so we're working on that. We've also looked at some other kinds of outcome variables. So what I've presented today is for continuous normal outcomes, but also have generalized this to ordinal outcomes, and then also time to event outcomes. And then I have a student who's just submitted a paper actually on count outcomes, and I'm working with a colleague at Northwestern, Junaid Sadiq, on gamma distributed outcomes as well. So I think that this class of models we can utilize for not just normal outcomes, but other kinds of outcomes as well. And just to give you a sense of some of the work involved in this area. Myself and some of my students, we've worked on various kinds of extensions. Some of them are listed here in this series of papers. But it's not just me that's working on these models of variability. So here is a collection of some additional papers and a lot of these are from the psychological area. That's an area where they do have a lot of interest in individual differences in modeling variance that maybe you can find interesting. So the point of this is just to show that I think there's a lot of possible applications for these kinds of modeling techniques beyond what I've illustrated today. So at this point, I'm happy to answer any questions people might have. That's all that I have.
Thank you very much for a very interesting presentation, John. I'm going to let the audience. I'm going to open the floor to the audience for questions. So if anybody has a question, can you either raise your hand or put the question in the chat, please? Okay. There we are, from Kaveri. Kaveri, can you please speak?
Sure, that was an excellent presentation. I'm not a statistician, I'm a physician and epidemiologist, and you explained it beautifully. I didn't understand everything, but I guess one of my questions is, so I mean, I think looking at variability is really cool. What I was trying to, and the reasons for it. So I found myself thinking that if you have an intervention, and I do behavioral interventions, you would, in order, if you demonstrate a difference between the means or a change between the two groups, then by definition, there would always have to be a reduction in variability in the intervention group, wouldn't there? Like, I'm trying to picture a situation where there wouldn't be.
It depends in some ways, on the outcome that you're looking at. For example, let's say, here's one thing that I've seen with physical activity. In physical activity, what happens, sometimes people come into these studies and they're doing nothing, right? I know,
I do physical activity studies and pedometer, so I know all about it.
Right?
Yeah.
Right. So in the start, the data are very consistent within subjects because they're mean of zero, variance of zero.
Right.
In that case, what you can find is that in the intervention arm, you increase the mean, and in that case, you could increase the variance rather than make it more consistent relative to the group that's doing absolutely nothing and staying at that consistently. So I think it depends a little bit on the measures. Now, you do raise an interesting point, though, that you raise a very interesting point that oftentimes the mean and the variance could certainly be related. I didn't present it here, but we have a parameter in the model that accounts for the correlation of the mean and the variance.
Okay.
Because, what I've modeled as well as what I've shown today is sometimes rating scale data. With rating scale data, you often see floor and ceiling effects. So that, for example, if a subject is indicating their mood, physical, say positive affect. If they're very high to the top, they almost have to be consistent. Very, very low to the bottom, they have to be consistent because of floor and ceiling effects. Okay. So the covariance of the mean and the variance will account for that in it. So we're getting these effects over and above that sort of intrinsic mean variance relationship.
Okay.
Okay. Teresa has a question.
Yes.
Yes, I think I've understood, as Kaberi said, not everything, but let me see if I get this right. What does measurement error, how can you take into account measurement error?
Yeah, that's
in different covariates that you're measuring.
Oh, in the covariates. Yeah, so that's, now here in these models, I don't have to worry so much about that because my covariates are just time, group time. There's,
yeah.
In other kinds of scenarios, one could have measurement error in the covariates.
Right.
You know, we haven't done that yet, but I gotta think that we could apply, you know, similar kind of the methodology, what's been done in regression models for measurement error of covariates, you know, and embed that within this class of model as well. So that would be an extension over what I've presented here.
Because you could also then have multiple measurement error issues.
Yeah, that's true. Yeah. Yeah. In some ways, I guess what in this, it's being absorbed in the variance parameters, presumably. Yeah. And you might want to separate that out as you say, that might be an important thing to separate out rather than not. If the, that's a really good suggestion.
Thanks.
Thanks.
I would like to ask a question.
Sure.
That is, actually, I have two questions. And the first is that, so, you know, you have all these linear models. You've got the linear models for the mean. Now you've got linear models for the variance terms. And I mean, of course, linear models are something that comes to our mind very easily. And I just wonder whether you've dabbled in machine learning methods. And I mean, it seemed to me like they can do more. I mean, that is, they can go beyond these linear models that we can sort of easily visualize and write a nice equation with. And I mean, I know it's beyond the scope of this talk, but I'm just wondering whether you, you know, as you're fitting this complex data, whether that's a thought in your mind, because, you know, it seems like these linear models are models we fit for decades. Maybe they work fine. And, you know, many times I just can't understand what machine learning is about.
Yeah, no, that's an excellent point. And we have used some of those machine learning models in EMA data for sure. Yeah, and actually this work I've done on this project, what we're looking at here is, can we use the random effects we get out of this modeling of the EMA data to serve as predictors of maintenance? And there we're using machine learning kinds of approaches, because we have like a binary, it's a classifications thing. Does a person maintain the behavior or not? And is there, you know, reaction during the EMA part to the physical activity? Can that predict the maintenance? So yeah, you're exactly right. That's a fruitful area to go further with this kind of approach, and other is really, yeah.
All right, of course. Yet there seems to be interest in the in using the kinds of models we've worked with for years, and that's very interesting to know. Like you say, it's nice to see all these you know, relations that you're talking about, how the within and between study variances, you know, connect and so on. The second question I have is in part what you just mentioned. So you're modeling the variance terms. You take the variance terms and then they are the outcome of a regression equation. What about the random effects themselves? Like if you think of, I think there's something called latent trajectory analysis.
Right.
What is that? How is that different from this?
Yeah. It's really, in a latent trajectory analysis, what it essentially, it's just like a model that has a random time trend in the model. And, and sometimes they classify those, and then that's called growth mixture models or trajectory models. But it's just, it's not unlike what's here, except it's focusing mostly on the random effects with, you know, the latent variables. It's thing, but again, they focus mostly on the random trend effects, and can you group those in terms of different groups and things like that.
Yeah. Okay.
So it's not a totally different sort of thing.
Okay. I'm sorry, I'm asking tangential questions to what you've presented.
Oh, no problem.
I guess what I see is that you have this very rich data, and there are so many ways that you can tackle it. And I like these models that you present because we understand them well, and it's a nice extension of what models worked with before. But indeed, it seems to me that something like that latent trajectory model is also trying to do what you're doing here. That is ask impacting the variance. Well, how does the variance?
Well, I would say this, the latent trajectory kinds of models are really more about, can you come up with classes in terms of the mean response across time?
Okay.
They don't
I see.
get
Okay.
at separation of subjects depending on the variance.
Variances. Okay. All right.
Yeah.
That's helpful to know.
One could do that, but I think in general, not so much. Yeah.
Okay. And the random effects, like I always feel like when we fit these mixed effects models, we estimate random effects and we don't do anything with them.
Right.
What could we do? I mean, it seems to me that that's important information over there. We just focused on those alpha 0, alpha 1, tau 0, tau 1 in your equations here. But
yeah.
What's
right.
Is there something in the random effects that you've spent time looking at? What can we get from them?
Yeah, no, that's a great comment. You're right. Most time people run these mixed models and, you know, they don't even look at the random effect estimates. And most software programs don't print them out unless you really ask for them. But I think they can be utilized. I mean, for example, in this context, it can, what it led to here, for example, when I would see these, you know, I plotted here the data of subjects that had the largest random effect of variance and the smallest, you know, I got this idea that, well, you know, here's a person that's erratic, but they're really only erratic at the last time point, that their erraticism kind of builds across time. And so, you know, that led to some other ideas that I wouldn't have thought about if I didn't look at these. You know, the other thing that what I found in other data sets using this approach is people that have large within subject variance, sometimes they have a few observations that are way out there, that are very unusual. So it's almost like an outlier detection procedure. It can detect subjects that have unusual variability, unusual observations. So I think they can be useful, but you're certainly right that they're not maybe used as often as they could be.
Can I ask one more question? This is really interesting.
Yes, go ahead.
I was just wondering if, so you had different intervention groups and it was almost a factorial design. They were like, you know,
Yeah,
groups.
yeah, it was.
Did you notice that erraticism for one behavior correlated with erraticism for another behavior?
Yeah, that's an excellent point. I think I'm pretty sure we looked at that.
Probably looked at it. Yeah.
Yeah, I don't recall, but you know what? But if you're interested in that, I had a student. Let's see if I have it in my list of where she did a bivariate model. Yeah, the student was Pugash. It was more in the nicotine tobacco world. She did a bivariate model where she's modeling the association in the variance as a function of covariance. So why is it that for some subjects they're very correlated and then for other subjects are not? So you're right. I think in most of these examples that I've looked at, oftentimes what I usually see, so I've looked at mood outcomes a lot, like positive mood, negative mood. If you run them separate, what you find is that, and you get to random effect estimates, if a subject is a high positive affect, they generally have a low negative affect in terms of the mean, which makes sense, right?
Yeah.
Their variance estimates are very correlated, positively correlated. So if they're highly variable on one mood, they're also highly variable on the other mood. And so I kind of suspect that might be operating with these behaviors as well, but I don't recall precisely. Yeah, that's a really interesting point.
Okay. Thank you very much. I'm not sure if I see any other questions, but thank you very much, Don.
Oh, sure, Andy. Well, thanks for the
There's a
invitation.
number of interesting points here today.
It was very nice to come to Montreal for an hour.